Wait, let me erase this one. That would be 6,430. Multiply that by, again, the distance of the distance of the centroid of the channel with respect to the neutral axis. So that would be basically D2. Okay? So that would be D2. If you were to write that down, if we cannot recall what you have written a while back, so that would be equal to 460, correct? 460 minus board Y. Okay? So that would be 460 minus 293.2662. Okay? So that would give you the value of Q to be 1072,098.334. That is in mm cube. Okay? Next is your maximum shear or your shear carried by the beam. That would be simply WL over 2. Okay? So you have calculated W a while back. So you have here V now is equal to 45.11 times your span is 9 meters divided by 2. So your answer here should be in kilonewton, since that one is in kilonewton per meter and that one is in meter. So that would give you 202.995. That is in kilonewtons. Okay? And then next is we can now have your spacing. Okay? So since you have now R, V, and then Q, you already have your I a while back. So you have now spacing now is equivalent to R, consistency of units. If that one is in Newton, you have Newton as your unit for force, and then mm for length. Okay? So you have here 40.2123 times 10 raised to 3. That is R. Next, moment of inertia. Moment of inertia is 970.6221 times 10 raised to the 6. That is your moment of inertia, Ri. Next is V. That is 202.995 times 10 raised to the 3. And then last is Q, 107.2098.334 mm cube. Okay? So your spacing here is equal to 179.3847 mm. That is on centers. Now, if you're a designer, of course, you would round this down, okay? For spacing, basic rule of thumb. So you would have here spacing is 175 mm on centers. Okay? Last required is to determine the theoretical cutoff point of the channel section. So basically, how do you get the theoretical cutoff point? Theoretical cutoff point is the point wherein your channel is no longer needed, and then the steel section or the wide flange section can carry the load. Okay? So how do we get that particular, or let's go back to strength of materials. Again, if you have here your steel beam, your built-up section, which is simply supported, okay, which carries a uniform load. Okay, uniform load, you have identified that a while back. W is 45.11, that is in kilonewton per meter. Okay, now if you were to draw the moment diagram for this one, skip the shear, just draw the moment diagram. Of course, moment diagram would look something like this, wherein your maximum moment is found at the midspan. Now, theoretical cutoff point is the point wherein your channel can be cut. Okay? And then, basically your section or your steel section or wide flange alone can carry the rest of the loads. Okay? So, if you were to have that principle, then this is the part wherein you would require a channel. Okay? And then the remaining part would be the part wherein the channel is no longer needed because the moment here is less than the capacity of your wide flange. So basically, you just need to calculate for the capacity of the wide flange and then locate it along the beam. Then you can identify therefore your theoretical cutoff point. Okay? So first things first is to get the capacity of your wide flange. Okay? So moment capacity of your wide flange is just simply make use of F bending is equal to MC over I. Okay? So you have here F bending for this one. Of course, you make use of the allowable bending stress for beam that is for the wide flange that is 138 newtons per mm square. M times C, what would be C? That would be half or mid height of the wide flange section, that is 470 divided by 2 divided by I. What is your I? I is Ix, of course, that is 726 times 10 raised to the 6. So the moment which you will be looking for along your moment diagram is equal to what? 138 is equal to 426.33. Okay? 19. Okay? Okay, now how do you get the location? You get the location by taking the section. Okay? Take the section, take this one as one free body. If you were to isolate that, take that as one free body, you would have here your section. Okay, of course you have your reaction here. Reaction for your support, which happens to be 202.995. We have calculated that a while back right here. Okay, next, of course, you have here your section. You have your shear reaction, and then you have your moment. Okay, now moment there is equal to 426.3319. That is in kilonewton meter. Okay, so simply by equations of equilibrium, you have 426.3319 kilonewton meter is equal to 202.995 times x. Okay, basically you're looking for this distance, that would be the lever arm for that one. You have your uniform load present on this particular section. Again, that one is W, which is equal to 45.11 kilonewton per meter. So going back, is on this particular rotation you have that one, and then on the opposite rotation you have minus, we have 400 or 45.11 times x over x, times x square over 2. Okay, so calculating for x, basically that is your theoretical cutoff point with respect to the support of your structure. So you have 3.3389. Now if you were to calculate for the length of the channel would be equal to 9 less 2 times 3.3389. L is equal to, or length of the channel is equal to 2.3222. That is in meters. Okay? So that ends the examples for the review of strength of materials which will be applied in steel design. That is all about shear and bending.